Hello, everyone. My name is Elahe Hayati from University of Arizona. And our first speaker is Festa Bucinca from City University of New York. And she will presenting remotely.
Hello, my name is Festa Bucinca. I am a PhD student at City University of New York. I work with Ari Mahler and Viviana Acquaviva, and recently we have been interested to know whether we can discover a physical model for galaxy sizes using a data-driven approach. So we know from observations that galaxies have sizes. These galaxies are rotationally supported, spheroids are pressure dominated, and some galaxies do not fit any of these models. From the theoretical point of view, we know that galaxies form as gas collapses within the potential wells of dark matter halos. And because of this initial mixture of dark matter and visible matter, both types experience similar tidal torques, which leads to angular momentum conservation. So a concise expression of this standard picture is the Moe, Mao, and White model for sizes, which says that galaxy sizes are determined by their parent halo's angular momentum, the R disk proportional to spin times R halo relation here. Unfortunately, there's no equivalent simple model for both sizes of film. So looking at recent literature on the topic, we see that in hydrodynamical simulations, there's no such a strong correlation between size and halo angular momentum. Most of recent literature on the topic says so, except for this last paper here. And so we ask whether we can discover a physical model for galaxy sizes using a data-driven approach. Now, our pipeline or our methodology here can be applied to any galaxy property, but in this project, we focus specifically on galaxy sizes. Machine learning tools are well equipped to tackle the complexity of such a problem because using them, we can learn whether or not the information is there. So in this case, whether the information about galaxy sizes is there or not. And we can learn if there is a small number of properties that contribute mostly to the prediction of the target, the property we want to know, like sizes. Next, we can perform symbolic regression to search for a mathematical equation that describes the relation between input and output, output being the property of interest. Semi-analytic models are a good setup to apply our pipeline simply because, unlike with data, in SAMs, we know the ground truth. And so, as a proof of concept, we apply this approach to galaxy sizes using the TNG 100 Santa Cruz SAM. TNG 100 Santa Cruz SAM is a SAM run on the dark matter only version of the TNG simulations. And because we know the ground truth, we know the recipe that sets galaxy sizes in SAMs, we are able at the very end to compare the physical model that we derive with the ground truth. To make all this test more realistic, we try to predict the half-mass radius, which is what is usually measured, rather than just the R disk. So we use two machine learning models to learn the benchmark for how well the sizes can be determined. And for that, we employ 31 galaxy and halo properties as features that we feed into our machine learning models, and we predict the half-mass radius size. Is the information there? So looking at the two machine learning models that we have used, the random forest model and support vector regressor, we see that yes, we can learn galaxy sizes with the help of these machine learning models. The random forest model seems to be very well at predicting the galaxy sizes. The R2 score, which is a measure of the performance of the model, simply a measure of correlation between true and predicted values, is 0.92 for the random forest model here. And with a more sophisticated model like the support vector regressor on the right-hand side panel here, the performance of the model gives an R2 score of 0.94, a slight increment, and also a less biased behavior in the predictions, which can be seen in the scatter plot. So with these two models, we are encouraged that the information is there and that we can move on to search for the physical model. So now that we know that the information about sizes in the 31 features chosen is there, we next ask if there is a minimum amount of features required for a good enough prediction. Why? Simply because we want to use this core set of features to then search for the physical model. And so we carry on an add feature ranking analysis where in the first line here, we run all the 31 possible one feature models, and we choose the one with the highest performing R2 score. So the feature with the highest performing R2 score is halo spin. We fix that feature, we keep that feature, and then we consider all the possible pairs with the first feature fixed, and then we choose the highest performing pair, and so on, until we run out of features. And so with this method, we learned that there is a set core of 6 features that provide a good enough prediction for galaxy sizes. In the plot here, you can see the R2 score increasing by the addition of each of the features until the 6th one, where it then saturates. So the 6 features that mainly drive the prediction of galaxy sizes in our data set are halo spin, stellar mass, entering via merger, stellar mass, rotation velocity of the disk, bulge mass, and velocity dispersion of bulge. Okay, now we know that there is this core set of features that drive prediction, so we want to search for the physical model. We start by using symbolic regression, a machine learning technique that searches the equation space for a mathematical formula that relates input and output. So symbolic regression equation search comes up with this physical model shown here. You can see that the spin times the R halo term is similar to the spin times R halo term that comes from the Mau and White model. And then we have a ratio of M bulge M star, and then this term 1 over V disk V ver. So all these variables make sense physically. And when we look at the performance of this model, we see that it isn't great. It is encouraging, but it's not great. We have an R2 square of 0.8 for this model. And then we see that there is some scatter in this region here. And so we ask if morphology could be related to the residual scatter. Because we expect physically that disks and bulges behave differently, we color code by morphology, and we see a noticeable gradient. So the red and yellowish dots here belong to disk and disk-like galaxies, whereas the elliptical galaxies are the blue and purple dots here. And so we see that the galaxies are well behaved. They follow the black line. However, the ellipticals are highly scattered. So with this, we are encouraged to now search for a physical model by morphology. So we again search for an equation by choosing a subset of pure disk galaxies only, where M bulge M star ratio is less than 0.1. And we use symbolic regression on this subset of galaxies. And the output of symbolic regression is the equations shown here, the spin over V disk V ver squared times R halo. The R2 square of this model is 0.92, which is an increase from 0.80 initially. And we see, however, that there are some galaxies for which the equation predicts smaller sizes, whereas the true size is constant. So we guess that there should be like a minimum effective spin that corresponds to these small galaxies. And so we adjust for this minimum spin, and we introduce a new term, the spin effective term. And then when we, with this new term, when we apply the same equation on the data set, we see that this new equation performs even better with an R2 score of 0.96. And then we do not have that problem that we used to have before. Okay, so now we have a functional form for pure disk galaxies. So next, we want to know how this functional form performs on other types of morphologies in our data set. So we divide our data set into 6 different morphologies. Group 1 here are the pure disks, the perfectly disk ones, and for each group, the M-bulge M-star ratio increases up until group 6, where we think that these are like elliptical galaxies, mostly bulge component. So in the first 4 groups, we see that the functional form provided by symbolic regression does pretty well, like in predicting galaxy sizes. However, it fails in the last 2 groups in what we call elliptical galaxies. Now, looking at the coefficient of this equation, C times spin divided V disk, V var square times R halo. Looking at C in each of these 4 groups, we see that C goes from about 1 in the pure disk galaxies to about 0.7 in these galaxies with a higher component of bulge. And so we guess that the linear term M disk over M star may effectively capture this decrease in the coefficient. And so we introduce the M disk M star term, and that becomes our fitting formula for the disk-like galaxies. So all the galaxies in groups 1 to 4, excluding the last 2 groups. And this way, we arrive at a point where we can combine our data-driven derived equation for pure disks with the additional M disk M star term from like human input for other morphologies, and come up with a final physical model for all disk-like galaxies. That is, for all galaxies with an M-bulge M-star ratio less than 0.4, color-coded here by the blue and greenish dots. And you can see that there are no red dots, no ellipticals in this plot. And so our final physical model is size is equal to 1.14 M disk over M star, spin effective divided by V disk V var square times R halo. The performance of this model is very promising. The R2 score is 0.96, and we can see that predictions behave pretty well. Is this completely data-driven? I mean, this is somewhat data-driven. There's some human input in deriving this equation. So we next ask if we got the right answer or not. We want to compare the ground truth model with our physical model. So the first equation here is the physical model from SAMS, and the equation below is the physical model that we derived. Both of these have the spin times R halo term in common, and so we want to compare the factor in front of spin times R halo in the 2 equations. So you can see that the factor in front of spin and R halo in the SAM equation is pretty long and complicated, whereas our factor in front of spin and R halo term is just 1.14 times 1 over V disk V var square. It's not the same thing, but we want to see if what we have derived is comparable to what the SAMs have. And so we plot this term in front of the spin R halo variables for both the cases, for the SAM and for the physical model that we have derived. The red line here is the factor in front of spin and R halo derived from the semi-analytic model, whereas the green dots correspond to the factor in front of spin and R halo in front of our physical model that we have derived. Both are shown here as a function of concentration. And so looking at this plot, we think that yes, we did get the right answer. Finally, we ask whether or not we have the information for ellipticals. So we look at the random forest learning curves for ellipticals, and looking at the green learning curve here for the test set, we see that there is an increasing slope. And so we see that we need more elliptical galaxies in our data set in order to be able to tell whether the information about sizes for ellipticals is there or not. And so there are two ways we can go around this problem. The first is by adding TNG 300 box, which is something that we're doing, we're in progress, because that has more elliptical galaxies. And the second is using some augmentation technique to obtain an equal distribution of disk and elliptical galaxies.
5 minutes.
In summary, yeah, the answer to whether we can discover a physical model of galaxy sizes using a data-driven approach or not is somewhat. Yes, we can use machine learning to learn whether the information is there, and we can use machine learning to learn which is like the small core set of features that drives prediction. And again, we can use symbolic regression machine learning to help us search for an equation, but we definitely need some physical human input in order to finalize that model. Thank you.
Questions?
Hi, Peter Baruzzi here. Thanks for a very nice talk. I'm looking at the 1 over v disk squared in the denominator, and I'm wondering if the symbolic regression has just relearned the circular velocity equation, which would suggest that the mass equals r times v squared divided by g. And so if I rearrange things, I can solve for r in terms of sort of the mass of the disk and then the velocity squared and constant. And so then I'm wondering if the information about the radius is in effect contained in the disk circular velocity, or the disk velocity in this case. And so that's what's being used to get the very nice match with radius that you found.
Yeah, I think that's a good way of thinking about it, because there is some information about radius that is somehow contained in the v-disk. So I thank you for like basically explaining what probably should be happening behind the scene, right?
Yeah, Swanson Ting here. So my question is quite like similar. So of course, like we can come up with some equation. So do you have any insights of how you would interpret the equation in general, right? So the symbolic regression by definition will come up with models, but like for the lack of like words, it's hard to call that physical models. So I just wonder, how do you make the connection between equation and physical? Is that like any guidance that we could use?
That's a good question. So I think like having the spin or halo and then m-disk and star variables, these make sense physically, but yeah, the hardest probably somehow to explain is the v-disk coming up and being able to capture so much information. Yeah, it's something we need to think about. Like,
More questions? Okay, let's thank Festa again.